Alright, so this is the review for Chem 104. I'm once again doing this during dismissal, so if you hear some announcements, I apologize. Alright, so the ideal gas law is Pv equals nRT. Alright, this equation is in your reference tables. And basically what we're saying is that if gas particles do not attract or repel each other, and they do not take up space, which of course they do take up space, then this is how they would behave. Now, no gas is actually ideal, but this is a way of us simplifying some math, and it actually usually works out pretty accurately. So now P is pressure, V is volume, N is the number of moles, R is the gas constant, and T is temperature. Now, over here is the values of the ideal gas constant. This is the R. But here's the thing. All three of these are the same, right? The difference is this one uses kilopascals for pressure, this one uses atmospheres, and this one uses milligrams of mercury. Most likely, you'll see this one for atmospheres. But you might need either one, and this information is also in your reference tables. Alright, so if you have a 2.0 liter closed container that holds 1 mole of an ideal gas at a certain temperature and pressure, which closed container, which of these four, will hold 3 moles of the same ideal gas at the same temperature and the same pressure? Alright, so how are we going to solve this? Well, the only thing we know about both containers is the number of moles. So let's rearrange this equation and solve for N. Alright, so now we just have N equals PV divided by RT. Okay. Now, the number of moles in the first container, we're going to call that N1. Alright, and so we know that the number of moles in container 1 is equal to the pressure of container 1 times the volume of container 1 divided by the gas constant times the temperature of container 1. The number of moles in N2, that's the second container, is equal to Pv2, because it's the second container, divided by RT. We also know that N2, this is the same N2, is 3 times N1. Alright, so now we're going to substitute. Okay, and we know that Pv2 divided by RT should equal 3 times Pv1 divided by RT. The 3 is coming from right here, right? And right now we're going to simplify. Our P's cancel, our RT's cancel, and that leaves us with V2 equals 3 times V1. Now we know that V1 is 2 liters because it tells us right here. So V2 equals 3 times 2, or V2 equals 6 liters. Alright, so that's how you would solve that one. Alright, here's another gas law question from a video. This is Professor Dave. Alright, and it says a 5.15 liter balloon has a pressure of 1.35 atmospheres. If compressed from 5.15 to 3.43 liters, what will be the resulting pressure? Now, pressure and volume are an inverse relationship. As one goes up, the other goes down. So I'm decreasing volume, that means pressure should increase. Alright, so we're going to start off with Pv1 equals P2v2. The pressure times the volume of one balloon, or the balloon at the beginning, has to be equal to the pressure times the volume of the balloon after compression. All right. So, and then we just put in our numbers. 5.15 liters times 1.35 atmospheres of pressure equal 3.3 or 3.43 times V2, because that's our unknown. That's what we're trying to find. So now we multiply these and we get 6.95 equals 3.43 times V2. And then we're going to divide both sides by 3.43, right? Because this is multiplying, so we got to divide so it cancels out here, and then we're going to divide over here. And we're left with 2.03 equals V2. Right. All right, for the second problem from Professor Dave, 0.785 moles of N2 fill a balloon at 1.5 atmospheres and 301 degrees Kelvin. What is the volume of the balloon? So with this one, we're going to use Pv equals nRT, the ideal gas law. And so we're going to say 1.5 atmospheres times the volume. We don't know the volume yet, so that's just V, equals the moles times the gas constant. Notice we made sure to use the one in atmospheres times the temperature. So we multiply all of this together. Our kelvins cancel, our moles cancel, and so we're left with 1.5 atmospheres times V equals 19.40 liters times atmospheres. So now we're going to divide both sides by 1.5. I don't know what happened here. That should say 19.4. There's some lag on my computer right now. All right, so 19.4 divided by 1.5, and we get 12.93 liters. All right, so that's how you do that one. This is another one that is pretty new. Equilibrium constant is the ratio of the mathematical product of the concentrations of the products divided by the product of the concentrations of the reactants that are in equilibrium. So basically, we're going to take the concentration of A times the coefficient, or raised to the coefficient, and B raised to the coefficient, and we're going to divide that into C raised to the C and D raised to the D. All right, so the exponents here are the coefficients from the equation. All right, now I'm not going to ask you to calculate this, but I am going to ask you to use it. So the equilibrium constant, if it's greater than 1, that means the products are favored. So more products are going to be produced. If the equilibrium constant is less than 1, then the reactants are favored. And all right, so more reactants are going to be produced. Now this question is telling us that they're at equilibrium at 200 Kelvin, and after equilibrium is established, the temperature is slowly raised. And additional equilibrium constants are determined in the data table. Now if you look, all of these have negative exponents. They're all single digit here, right? And they're all negative here. So that means we're going to have, this is really 0.03. This is really 0.01. This is really 0.004. And this is really 0.0005. All right, so that's a really small number. All right, and so what we're going to do is we're going to take this knowledge right here, and we're going to say, hey, if I want the greatest concentration of product Z, and Z is a product, then I need the equilibrium constant with the largest number, all right, that's closest to 1. And the one that's closest to 1 is at 200 Kelvin. So that's the answer, okay? Make sure you know that matter cannot be created, nor can it be destroyed. This is another new one. So you're familiar with the pH scale. 0 to 6.9 is an acid, 7 is neutral, 7.1 to 14 is a base. Okay. Now, the pOH scale, right, which is a measurement of the hydroxide concentration, is kind of the flip of that. It's like the bizarro pH. So 1 to 6.9 is basic. Actually, -1 to 6.9 is basic. 7 is still neutral, and 7.1 to 15 is an acid. But all you really need to know to answer this question is that pH plus pOH equals 14. Now it tells us that the pOH is 12. So if pH plus 12 equals 14, then 14 minus 12 is 2. The pH is 2. So the answer has to be A or C. And then we remember that any pH less than 7 is an acid. So the answer is C. It has a pH of 2 and is an acid. All right, here remember that the group tells you the number of valence electrons. So everything in group 1 has 1 valence electron. Everything in group 2 has 2. Everything in group 13 has 3. Everything in group 14 has 4. Everything in group 15 has 5. Everything in group 6 has 6. And everything in group 17 has 7. Okay? Everything in group 18 has 8, except helium. It only has 2 electrons, but it's still a noble gas, so we let it hang out there. Okay? Nitrogen is in group 15, so it has 5 valence electrons. Magnesium is in group 2, so it has 2 valence electrons. Carbon is in group 14, so it has 4 valence electrons. Okay? Ion is a particle with a charge. A positive ion is called a cation. I remember this because this is a plus and a T kind of looks like a plus. So ions are positive ions are cations. Negative ions are called anions. Okay? When electrons gain energy and move up to a higher orbit, we call that the excited state. And we could call the process excitation. We're exciting the electrons. Now, when those electrons lose that extra energy and fall back down to the ground level, we call that relaxation. And that's it for Chemistry 104. I'll see you in class tomorrow. Have a nice day.